At the end of the instructions for the previous exercise, I asked the question, does reconstructing the image using the first four components or the first four SVD layers give a good result like it did in the previous chapters? And I start exercise 11 here by saying the answer is no. Absolutely not at all. The rank 4 approximation looks terrible. It looks nothing like the picture. Okay, so now what we are going to do in this exercise, exercise 11, is basically repeat the same thing. So using the same code, you can copy and paste the code into a different cell. But now I want you to use 80 components, so the top 80 components instead of the top 4 components. And you will see that it looks like this. So here's the original picture. Here's the reconstructed with the top 80 layers summed together. Now, this obviously looks really, really good, right? Compared to, let me go, this. I mean, this is the first 4 layers, and here is the first 80 layers. And then what you can do here is compute the squared error image. So essentially, that's this image minus this image, literally pixel for pixel subtraction. And then you square the errors. And the reason why we square them in these kinds of analyses is because we don't really care if the pixel value, this one pixel value here, if that's a little bit too small or a little bit too large. We just care if it's off. We just want to know if it's an error and the magnitude of that error. So here you see an image of the squared errors between the reconstruction and the original. Pretty interesting to see that, the errors are very low in all of the kind of flat parts of the image. So everywhere where it's solid white. And, there's the higher errors where there is sharper contrast, where there's contours and a lot of things happening in the image. Okay, so that's part of this exercise. Another part of this exercise is to compute the compression ratio. So now the idea is that by taking the SVD, we can project out a lot of dimensions in the data that are not necessary for understanding the data. Now, to be sure, this isn't a rank 80 matrix. This is a rank 430 matrix. So we have lost some information. This is a representation of the image of the information that we have lost. But, the question is not whether we have lost any information at all. The question is whether we have lost important information. And here the answer is clearly no. We can identify this picture with no problem. So yeah, this information that we have lost is fine. So given that, we want to compute the compression ratio. And that's literally just, you have to figure out in Python how to get the sizes of different matrices, how much memory they take up. And then you can see that the original image is 2.10 megabytes. So this image here in Python is 2.10 megabytes. Now, here's the thing. This image here is also 2.10 megabytes, right? It's exactly the same matrix. It's the same size. It's the same data type. So of course, it's exactly the same amount of data that it uses up. But when we are doing these reconstructions, you don't need to store all of these pixels. You only need to store the first 80 singular vectors, the first 80, the first 80 left singular vectors, the first 80 right singular vectors, and the first 80 singular values. And when you just look at the how much information is stored in all of those 3 items, then in this case, that turned out to be 0.65 megabytes. And so basically the ratio between these is 31%. In other words, we haven't really changed the image recognizability at all, but we now have a representation that is 1/3 of the size. So 31% of the size. You can imagine, trying to send this to someone as an attachment for email. It's better to send this than this. Okay, so now I'll switch to code and show you my solution. So I set this number of components here to be a parameter. That's good for soft coding. It's just generally good coding practice. But I also did this for you so you can explore different numerical values. You can range this from between 1 and 430 and see how it looks. So here's the reconstruction. We use the first k left singular vectors, the first k right singular vectors, and the first k singular values. And then it's just a matrix multiplication. Of course, if we set this to be 430, 4,300, but 430, then yeah, I mean, then that's the same thing as just multiplying out these matrices like this, which you have seen many times before. So here we know that this is going to be a perfect reconstruction. Okay, let me set all of this back. All right. So let's see. So then I show, okay, so here I'm just showing the images. So here is the original picture, the reconstructed picture, and here I compute the pixel-wise difference, and then I am squaring those. All right, so here you see the original, here is the reconstructed, and the error map over here. And now actually when you look at it in a slightly larger zoom than what I have in the book figure, you can see that this is a little bit rougher, right? This is more high contrast. We see the contours a little bit better here, and this is a little bit smudged out, but still easily recognizable. In fact, this just looks like a compressed version of this image. Okay, and so to get the sizes of these different matrices, you can use a method on a variable called bytes. So strav.n bytes. And then this is the total number of bytes. So then I'm dividing by 1024 squared to give me megabytes. Okay, so then we see, yeah, same thing I showed before. So, right, so the idea is that the original image and the reconstructed image are the same size. But if you wanted to transmit this information, you don't need to transmit the image. You just transmit only the numbers in the SVD matrices that you need. And that is the first K columns in U, the first K elements in S, or the singular values, and the first K rows of V transpose. And then we sum these together. And so, yeah, that gives us the size of the compression and then the compression ratio.